This last example, I want to go over a problem where the thermal energy change or the internal energy change is not negligible and we do have some heat transfer. So this is kind of a problem that will bridge fluid mechanics and thermodynamics. So when you start doing your thermodynamics classes, you can think about how this type of problem works into what you'll be doing in that class. All right, so the problem statement is that a turbine receives steam at a pressure of 2 megapascals, a temperature of 500 degrees C, which yields an enthalpy, which is equal to U plus P over rho of 3,062 kilojoules per kilogram at a velocity of 10 meters per second. Steam exits the turbine at a pressure of 101 kilopascals, a temperature of 100 degrees Celsius, yielding an enthalpy of 2,621 kilojoules per kilogram, with a velocity of 50 meters per second. The thermal energy loss is 5 kilojoules per hour. We're told we can neglect potential energy change and head losses. And for a mass flow rate of 4,000 kilograms per hour, which is 1.1 kilograms per second, we're asked to find WT dot. So we're given a diagram here. We have an inflow coming into the system. The enthalpy is 3,062 kilojoules per kilogram and a velocity of 10 meters per second. And then going out of the system this way, we have an enthalpy of 2,621 kilojoules per kilogram and a velocity of 50 meters per second. We have the energy losses due to heat transfer. Q dot is equal to negative 1.39 joules per second. So I've just converted that from kilojoules per hour to joules per second. And we're asked to find WT dot there at the bottom. Okay, so the first thing we do is label our two endpoints that we're going to use our conservation of energy between. So point 1 here on the left and point 2 on the right. And then we'll write out our conservation of energy in its full form. So we're going to get Q dot over M dot G plus P1 over gamma plus Z1 plus alpha 1 V1 bar squared over 2G plus U1 over G plus H sub P is equal to H sub T plus P2 over gamma plus Z2 plus U2 over G plus alpha 2 V2 bar squared over 2G plus H sub L. Okay? And just like all of the other problems we've done, the first thing we want to do is try to get rid of some terms. So we know Q dot, so we need to keep the first term. We know the pressure, we need to keep the second term. We're told that Z1 and Z2 we can neglect potential energy, but the way it's drawn, they're the same. So we can say Z1 is equal to Z2. Okay. Alpha 1 V1 squared over 2G, we're given V1, so that's going to be important, but we're not given any information about alpha. So we can assume alpha is equal to 1, so we can get rid of that. We're told that the temperature changes between the two, so U1 and U2 are going to be different, so we need to keep those terms. And there's no pump. Okay, there is a turbine. P2, we are given a pressure there, so we know that that's going to be important. We know the temperature changes, so U2 is going to stay in there. Told nothing about alpha, and we are given a velocity, so we assume that alpha is 1. And we are told we can neglect head losses, so that term goes to 0. Okay, so that simplifies this a bit. The next thing we want to do is multiply through by M dot G. And the reason I'm going to do that is because of the fact that we're given this term enthalpy as a combined U divided by, U plus P over rho, sorry. All right, and by multiplying through by M dot G, I'm going to be able to rearrange some terms to get that into a form of a quantity we know. Okay, so let's do that. I'm going to rewrite this equation. After multiplying through the entire equation by M dot G, I'm going to get Q dot plus M dot times P1 over rho 1 plus U1 plus V1 bar squared over 2 is equal to H sub T times M dot G plus M dot times P2 over rho 2 plus U2 plus V2 bar squared over 2. All right. And so what you see here is by doing that, now I can replace these two terms on both sides. This is now the enthalpy. You'll learn more about enthalpy when you take thermodynamics, but here you're told that it's U plus P over rho. It's a combined kind of pressure and temperature energy, and measure the internal energy in the system. All right, but now from here, what we do is we've been able to combine those terms, and we actually have values for those numbers, so we can plug that in directly. Okay, so now we can actually plug in everything and solve for WT. And so you're probably asking yourself, so where is WT? Well, remember from our definition of WT that this term here, H sub T M dot G, is WT dot. So this is what we're interested in solving for. All right. So we can plug all our numbers in, and we get negative 1.39 joules per second, we're given Q dot, plus 1.11 kilograms per second, that's M dot. The enthalpy is 3062 times 10 to the third joules per kilogram, that's the enthalpy, plus 10 meters per second, square that, over 2, minus, sorry, I'm going to 1.11 kilograms per second. So I've just moved the part of the term here to the other side of the equation, times 2621 times 10 to the third joules per kilogram plus 50 meters per second squared over 2, and that is all equal to WT dot, right? So what I did is I just moved this part of the equation to the left-hand side, so I'm left with WT dot on the right-hand side. Okay, we can plug that into our calculator. We get WT dot is equal to 488 kilowatts. Right, so it's a pretty stout device. That's quite a bit of energy. If you think about a light bulb is 100 watts, then this is 488,000 watts. So it's quite a bit of power. And this problem again demonstrates that connection between mechanical and thermal energy that you'll deal with a little bit more in your thermodynamics class. All right, so in our next video, we're going to move on to a different topic, and that's going to be dynamic similarity, similitude, and the use of non-dimensional numbers. I'll see you soon.